We're going to use an iterated integral to find the volume of the solid enclosed by the paraboloid z equals x squared plus y squared plus 1 and the planes x equals 0, y equals 0, z equals 0, and x plus y equals 2. Let's look at the region in the xy plane. In the xy plane, we're bounded by the y-axis, which is x equals 0, the x-axis, which is y equals 0, and the line x plus y equals 2. That line has both its x and y intercept at 2. So we have this isosceles triangle in the xy plane, which I just realized would probably be better if I gave it a little bit of color. Not so much for its own sake, but because we're about now to try to visualize this thing in R3. This green triangle in R2 translates to a similar triangle in R3. It's still in the xy plane. And I can make it green there too. Now here we're bounded by the z-axis, but we're also bounded by the paraboloid z equals x squared plus y squared plus 1. You may recognize that as a paraboloid that is up 1 unit on the z-axis, centered along the z-axis. And the solid that we're talking about is the region under the paraboloid and above the triangle, which I am not going to try to draw. The picture in R3 on the right gives us the height, or really our integrand. And our integrand is x squared plus y squared plus 1, technically minus 0 because the lower limit for z would be 0, but we'll just go ahead and leave that off because we don't technically need that. The region D in the xy plane is what gives us limits of integration. We have the choice of using dx dy or dy dx. I will go ahead and go with dy dx. So let's do this. I want you to set this up using the order of integration dy dx. Use the region D to figure out your limits. Go ahead and integrate it and then come back when you're done. How did it go? Based on the region D here, I can see that y goes from 0 to the line, which is given by y equals 2 minus x. So y goes from 0 to 2 minus x. X goes from 0 to 2. That gives us the integral for the volume. That volume is equal to the integral from 0 to 2 of the integral from 0 to 2 minus x of the integrand quantity of x squared plus y squared plus 1 dy dx. Integrating with respect to y is going to give us x squared y plus 1/3 y cubed plus y. We're going to evaluate y from 0 to 2 minus x, and all of that is in the integral from 0 to 2 dx. Substituting 2 minus x in place of y is going to give us x squared times the quantity of 2 minus x plus 1/3 times the quantity of 2 minus x cubed plus 2 minus x, and substituting 0 in place of y zeroes out all the terms. I made here a little note to myself that x squared times the quantity of 2 minus x is 2x squared minus x cubed, so that I can just take the whole thing and integrate using the power rule. That 2x minus x cubed integrates to 2/3 x cubed minus 1/4 x to the 4th. And then here this term 1/3 times the quantity of 2 minus x cubed, I can just use the power rule on that, recognizing that I have a du of -1 because my u is 2 minus x. So that integrates to the term here, -1/12 times the quantity of 2 minus x to the 4th power. And then the last two terms, 2 minus x, integrate to 2x minus 1/2 x squared. This whole thing is evaluated from 0 to 2. Putting 0 in place of x is going to give us 16/3 minus 4 plus 4 minus 2. And then putting 0 in place of x is going to give us minus a -4/3 here. And I realize I don't want to write it this way. We were supposed to find the volume. And so I'm going to write the answer as v is equal to our answer, which is 14/3. This, of course, would have had to be positive if we're looking for a volume. In general, though, iterated integrals can evaluate to a negative number. If they do, it just does not mean volume. Next is something a bit different. Sketch the region D and reverse the order of integration. We're given the integral from 0 to 2 of the integral from x squared to 4 f of xy dy dx. The innermost integral with limits x squared and 4 correspond to the first differential dy. So we know that y will go from x squared to 4. And then the outer integral tells us that x goes from 0 to 2. I'm going to turn that into a graph in the xy plane. Here we have an arc of the parabola, y equals x squared. We're bounded above by y equals 4. And since y goes from x squared to 4, we're talking about the region along the y-axis there. And x, of course, goes from 0 to 2. Well, this curve, given as y is a function of x, is y equals x squared. But if we need to reverse the order of integration, we need to express this as a function of y. And so x is equal to the square root of y. Because the region is along, it touches the y-axis, right? It's got the y-axis is one of its boundaries. We know that x is going to go from 0 to the curve square root of y. So reversing the order for dx, x goes from 0 to the square root of y, and then dy is the outer differential. It goes with the outer integral because we've reversed the order, and y goes from 0 to 4. Our integrand was just given as f of x, y, and so we are done. Folks, sometimes I put something like this on a test and somehow someone gives me a numerical answer. There's not even a function in here. We have f of x, y, that's the integrand. It needs to be there because we didn't change what we're integrating. We just reversed the order of integration.